Okay. All right, so interesting week. We have class Wednesday, Thursday, Friday. Okay, I just got a room for Friday, so I'll send that to you guys. It'll be Friday morning at 9:30. Okay. Assignment, I posted that last Friday. It'll be due this Friday. Okay, it should be pretty straightforward based on the stuff we did in class. Let me know if you have any questions. Any other questions about anything at this time? Okay, let's remember where we were. We had just done the ideal gas law, right? We did a simulation of a bunch of particles in a box, and the particles were non-interacting. And of course, this is the ideal gas, right? Where you have a bunch of particles in a box and they don't interact. Okay? To make things more interesting, let's take it one step further. We'll have a non-ideal gas. We're going to have the particles interact with each other. And we're going to have the easiest interaction we can have. There's not really going to be an attraction between the particles. And there's not going to be a repulsion where they like to stay away from each other. Again, they don't like to stick together. Instead, we're just going to have, they can't penetrate each other. Okay? So we want some kind of wall type force in there so that when two particles are on a collision track, they don't go through each other, but they bounce off. All right?
Do that same as repulsion.
It's hard wall repulsion. Okay? So they only repel each other when they try and go through each other. Okay? But it's not like having two positive charges that repel each other, you know, even when they aren't in contact. Cool? So this is called excluded volume. A particle can't go where another particle already is. Okay? So that's the interaction we want to build. Cool? Okay. Well, how are we going to do that? So what we want is a system where previously our particles could go through each other, but now we want it that if they're on a collision course like this, they bounce off of each other. Okay? So this guy's bouncing off like this, and then this guy, let's say, would take off like something. Okay? We want to build this interaction into our system. And for now, we're still going to have the same thing at the walls, where we simply reverse the direction, okay, of the velocity. So if we ever find the particle outside of the box, we just reverse its velocity. Take care of it. Cool? Okay. So this is an excluded volume interaction that we want to build. So there's a couple of things we could do. We could kind of do what we did with the wall, which was basically what we're doing with the wall is we're using conservation of momentum, right? If you have a perfectly elastic collision between some object that has some mass and another object that has infinite mass, the one object just bounces off of it, right? It'll have the same velocity but in the opposite direction. Cool? We could do the same thing here. We could look at our simulations and try, and we can calculate when these two particles are going to intersect with each other, and we could just do our conservation of momentum to give new velocities to each of the particles. Okay? This is event-driven simulations. We don't want to do that here. Okay? We want to stay firmly within the realm of pure molecular dynamics for now. And so remember what molecular dynamics says. Molecular dynamics says the sum of the forces on particle I, is equal to the mass of that particle I times its acceleration. And what we're doing in molecular dynamics is saying we can use this to calculate the acceleration of the particle. And from the acceleration, we get the velocity. And from the velocity, we get the new position by numerically integrating. Cool? So the beautiful thing about molecular dynamics is that if you can find a way of expressing your interaction as a force, all you need to do is include it into this sum here, and the rest is taken care of. Cool? All we need to do is write down some kind of force that corresponds to our excluded volume interaction. All right. Yeah? We're all on board? Okay. So how are we going to get a force? Well, first let's talk about a very famous potential. Leonard-Jones 6-well potential. Okay? And it has a form that looks like 4 epsilon sigma over r, and that's all to the 12, minus sigma over r all to the 6. Okay? Very, very famous potential. Have you guys seen this before? Okay, this is what it looks like if you plot it. We'll look at plots in more detail, but let's just do a kind of qualitative assessment for now. So what is sigma? Sigma is the size of the particle. Okay? And that is where you have this well depth here. Okay? Sigma is the effective size of the particle. And epsilon is this well depth here. And so the idea behind this potential is this. You have 2 particles, and they're separated center to center by some distance r. There's a potential energy associated with the interaction of these 2 particles. Okay? So if they're infinitely far from each other, what do you expect the energy of interaction to be? 0. Okay? As they come closer together, these particles have an attractive part. Okay? So the potential energy actually decreases as they come closer to each other. Cool? But if you try and get them too close to each other, you start to overlap them, then there's a very steep repulsive part to the potential. Okay? That is the 12. Okay? And so the way you can think of this is even if you have 2 neutral atoms coming together, okay, then they have a positive core, a cloud of electrons around them, right? As you bring them closer together, does anybody know what happens? Since they're neutral, is there no interaction? Because obviously we have a positive charge and a negative charge that stick together. We have a positive charge and a positive charge that repel each other. But what if we have atoms like this, where they're overall neutral, but there is a charge distribution? Does anyone remember what happens?
The higher terms in the multiple expansion.
That's right. Okay. Because what can happen is that as you bring these closer, you can say, okay, this guy at some point in time has a charge distribution where the electrons are more on this side. So the closest part of it seems positive. That's going to pull some electrons here. And so that this guy would have a dipole moment, points like this. This guy has one that points like this. Okay? And so you would get a dipole-dipole interaction. Cool? The dipole-dipole interaction, you do not need to know the details of this. Okay? This is historically where Leonard-Jones comes from. The dipole-dipole interaction, a dipole goes as 1 over r cubed, okay, the potential, and the dipole-dipole interaction then goes as 1 over r6. Cool? So that's where this r6 attractive part comes from. Notice that's the negative, okay, the r6. Cool? But then we have this problem that if we just have this dipole-dipole interaction, eventually these atoms will sit right on top of each other, and we know this can't be true. Okay? If you were at the modeling seminar last week, you know why this can't, one of the reasons why this can't be true. Okay? Pauli exclusion principle. Okay? So, what do we do to take care of that? We do something totally ad hoc. We just throw in a strongly repulsive potential, and we make it to the r to the 12. Why do we make it r to the 12? Because that's r to the 6 squared. And so it's easy to calculate in our program.
That was how they derived it?
Pretty much. There's no real justification for that, except we can't let these overlap too much. Okay? Cool? In fact, some potentials will have like an exponential decay instead or something. Okay? We good with that? Okay? So this is just a qualitative motivation of where this potential comes from. Okay? You don't have to worry about the details about, you know, multipole expansion of the distribution of charges. Okay? That's where this comes from. And because It comes from there. It is totally ubiquitous in simulation packages, okay? But it's not what we need. Do we want an attractive part to our potential? For our non-ideal gas, remember, all we want is for them to bounce off of each other. We don't want them to be attracted to each other so that they get around some distance, do we? Yeah? No? No, we don't, okay? The crowd says no. How can we get rid of this attractive part? For those of you that know, let's give a chance. This is the potential we have. We want to get rid of this attractive part here. What can we do?
But you want it not attractive, the same shape?
Well, you can do whatever you want to this potential here. But I don't want you to introduce a new potential.
You just don't want any attraction.
That's right.
Shift it up.
Shift it up. So if I shift it up, it's going to look like that, right? Okay, I got rid of the well. It doesn't go below 0 anymore. But if I'm coming in from infinity, now these charges, right, it's not going to 0 anymore. So I shift it up so that there's no negative part, and what else do I do?
We're not allowed to change it. They change the form of the potential.
No. Because that's in the packages. Let's just cut it off here. Okay? We only implement this interaction when the particles are closer than this distance. Cool? And we shift it up so it's not negative. All right? So we can write down the modified Leonard-Jones potential. And this is known sometimes as the WCA potential for the three guys who did this, Weeks, and Anderson. It's sometimes called the shifted and truncated Leonard-Jones potential. We'll use WCA here for convenience. Okay, and so we just shift it up by epsilon. All right, and we only implement calculations of potential when the particles are within RC of each other. Okay, and I kind of lied to you. The minimum here is not sigma; it's slightly different than sigma. Okay, RC. I'll leave this as an exercise to calculate the minimum. Obviously, what you do is you take the derivative with respect to r and minimize it, is at 2 to the 1/6 sigma. Cool? So this is an incredibly ubiquitous potential within simulations of particles. Okay? Certainly coming from the MD realm of things. Okay.
Why would you not want a repulsive or an attractive?
Oh, you can.
Okay.
Yeah, but we don't, because the only thing we want to introduce here is excluded volume.
If that is. Okay.
Right? So we can do that. We can do simulations of a gas that have an attraction, right? And we will totally talk about that in a minute. Okay?
But are there physical systems where there's no attraction?
Yeah, non-ideal gas, right?
Non-ideal?
Yes. And a gas that both has, non-squared ideal gas, okay? A gas that both, we include the excluded volume and we include the dipolar gas.
Yeah, but so this one that we're going to do has the excluded volume without the dipolar.
That's right.
So is there a physical system that corresponds to that?
A bunch of bouncy balls.
Right, yeah. Oh, we can simulate play them.
Yes, you can. That's the final program.
Oh, good.
Yeah. Okay, any questions on this? We're all good? Okay, there's a problem. I've been talking about a potential. What does our MD simulation need? Force. How do we get a force from a potential? Anyone remember?
Potential?
Yeah, okay. So you have a conservative potential energy, the force is negative, the gradient of that. Okay, so our WCA force then is just negative the gradient of our WCA potential. Cool. And to get the gradient, in this case, because this is a central force, it's really only a function of r, and then you just have to take the different components in x, y, and z. Okay? Yep.
So the thing that comes to mind immediately, and it's definitely nitpicky, but if you have three particles interacting at once, then it's not only the top and if you have three particles within 632 sigma, then the potential each of one of them felt would be also.
No, it's pairwise. You just have to do it between every pair of particles. Just like with electric charges.
Do we have superposition here?
Yeah. We'll see that. We'll do simulations of multi-particle systems. You can just pop this through. You just have to make sure you look at every pair of the system, which is where it gets expensive. Cool. All right, everybody okay with this? Yeah? All right, so our work here is done. We now have our force that we can include in our simulations as part of this sum here. All right, and now we're going to have excluded volume in our simulations. Cool. So we'll have a non-ideal gas where we include excluded volume, and no attraction. Good. Okay. So before we look at the simulations, let's just look at the theory side for a second. Oh, one important thing about this. The force being the gradient of the potential, why is it important that we cut off the force here at the bottom?
Gradient.
It's defined. What's the gradient at a minimum? 0. Okay? So what's going to happen in the potential is the force is negative the gradient, right? So here, if we have two particles that get this close, this is a negative gradient, so we're going to get a large positive force pushing them apart, okay? As they get further and further apart, the force decays, and we cut it off exactly where the force equals 0. So this means we don't have any discontinuous steps in our force. Okay? If we cut it off, let's say here, we would go from 0 force to some finite force. Okay? Cool? All right. So let's just look at the theory side of this for a second. So previously, remember, we had the ideal gas, where these particles, even if they were on a collision course, could go straight through each other. Okay? And we said P, pressure is still going to be our observable in our simulations, is equal to NKT over V. All right? Are we going to have to modify that at all for our new system where they bounce off of each other? What do you think changes there? Anything or nothing? Do you still expect this law to hold true? Any comments on that?
Before we said pressure was collision with the wall. So I think that.
Pardon me?
I think it would still.
Okay, we have a vote for still holds. Any dissenting opinions, Amber?
No, I don't have the dissenting opinion. Because the only thing I can think of is if they both at the same time are involved, then it would just double, right?
Yeah.
So,
I mean, that can happen in the other case too, right?
well, can it though? Because they would like hit each other in that way, right?
Okay, so what do you mean when they both hit each other? Sorry.
So if they both were headed in the same direction of the wall, and they hit each other at the wall,
Mm-hmm.
I guess there'd be less friction in that case. Whereas in the other case, they would go right through the wall. The pressure would increase.
So you're saying it will or won't work?
I guess now I'm saying it won't be the same.
Okay, and you expect the pressure to go up or down?
Down.
Down. Okay. So we have pressure stays the same, pressure goes down. Any other opinions?
Well, you could argue that the pressure should go up because the excluded volume is removed from the available volume. So you still have the ideal gas law. You've now effectively reduced that.
Right.
In other words, thank you.
Yeah, so N doesn't change, KT doesn't change, but how about V? Okay, here, each particle sees the whole box, right? Because it doesn't see any other particles. But over here, this particle sees the box minus this particle. That volume is not accessible to it because we have excluded volume, right? And so the V then, we can modify to be, can't, right there you guys can see it on the So let's write that as B tilde here, okay? And so that's going to be our old V minus oh yeah, this is tricky. Okay. Minus some term, okay? Let's figure out what that term is. Well, the volume of a particle, what's the volume of a sphere? And so R is sigma over 2, right? Sigma is the diameter. Okay. And so what we would be tempted to write in here is V minus N times this VP, volume of the particle.
But it's not hard.
It's pretty hard. Yeah. This increases as R to the 12.
It's enough to say that it's a hard one.
Yeah.
That it's a sphere.
Yeah. Because if you actually plot this thing out, when it looks like this, okay, the cutoff is at 2 to the 1/6 sigma. Okay, but sigma is over here, a small shift away. This is actually like 1.16 or something like that. And if you trace this back, that's equal to 1 kT. Okay, so sigma is a point at which the overlap energy equals the thermal. And to get any more overlap than that, it skyrockets. Okay, so sigma is a good effective radius. Cool. Is there any other problem with this? It's a tricky point.
They can't get within 6.
Austin, do you have anything to say on this?
Sure. You were kind of over there. There's the thing you have to consider the cutoff points. We still have to consider the cutoff point for 6.
So I have a sphere here, right, of size sigma. And I have another sphere over here, okay, that is excluded from entering this, right? So I want to know, I'm going to measure where the center of this particle could be in the box. Okay, all the space available to the center of the particle. It's not that the center of the particle is excluded from this guy here, right? Okay, the center of the particle can't get, it's not just that it can't get inside of this sphere here. Okay, the center can't even get this close. Right. Okay. So we have an extra factor, 4. It's a good question. Because we're in 2D. Yeah. So in 2D, the volume we've been talking about is pi r squared, right? And so this factor of 2 gets squared and we get 4. Okay, in 3D it would be a factor of 8. Cool? All right, is everybody okay with this? So our new ideal gas law then, okay, and let's write it in 2D now. So let's do area 4n times the area of the particle.
So this doesn't account for the wall.
No, we're ignoring the walls for now. Okay, this is okay with everybody. So when we excluded volume interactions, do you expect the pressure to go up or down? It's going to go up, right? Because your denominator is getting smaller, which means your pressure is going to go up. The reason it's going to go up, previously, if you had 2 particles on a course, right, they could just go through each other, right? But now, let's say you have a particle near a wall. It hits a wall, bounces off, hits another particle, hits the wall again, hits the wall again, okay? There's going to be way more collisions with the wall due to these excluded volume interactions. Yep.
I was just wondering, we did all the work to figure out the tilt down. So we plugged in areas instead of the bottom.
Yeah, I switched from 3D to 2D on kind of on the fly. Okay. So my argument was based in 3D, but I want to implement it in 2D because we're going to do a 2D simulation. Okay. I need to fix that in my notes.
Yeah, so the
You
volume.
guys are the guinea pigs.
What's A and what's AP?
A is the area because we're 2D. So
Yeah.
the area
Total area that.
and then AP is the area.
I was just wondering about that.
No, so we don't use CP3, A.
Yeah, I know that.
Yeah, so just instead of R, like, it's before like, before we were treating it like, I could think the center of it is still a particle, and it's a bunch of particles.
Let's table that for later. Okay? Let's keep going. You okay enough to keep going?
Yeah.
Yeah? Okay. So this is very close to what is known as the van der Waals equation of state. Okay? Because what we're very close to trying to simulate here is a van der Waals gas. Okay, and the van der Waals equation of state is P times V over N minus 4 volume of the particle. No, sorry, that's not right. Is P plus A times N squared over V squared. And V over N minus B equals K2. Okay. And in this definition, you know everything except A is some measure of the attraction between the particles. And B is a measure of the excluded volume, which in this case means that is equal to 4 AP, area of the particle. So Martin, here's your question. Can we do a gas with attraction? Then we can have the A. Okay? Now, this doesn't work particularly well, but it's a useful form to introduce ideas we just talked about, excluded volume and attraction. The attraction part doesn't work very well, but actually the excluded volume part, if we just take A and pop it equal to 0, I'll leave it as an exercise, you're going to get this form for the pressure. Okay? So it accounts exactly for the excluded volume in the way we would suspect. You just subtract off the excluded volume of all the other particles. Cool? Yeah? Okay, so let's see if this works.
In our case here, small a is 0.
Yes, A is equal to 0. Because we're not going to have cut off the thing, so we don't have any attraction. Okay, so when we go to implement this, we're going to see a couple of interesting features. Okay? So this is very much the same as the code we've seen so far for the 2D, for the ideal gas where there are no interactions. We're just going to introduce a couple parameters here. We're going to set our epsilon to 1 and our sigma to 1 because we like to set everything to 1 wherever we can. Cutoff radius is 2 to the power of 1/6 times sigma. All right, the rest of us we don't really need. Now, when I go to initialize the system, remember what I did with the ideal gas. I could just throw particles anywhere within the box, right? Well, what's going to happen now if I throw two particles that have a huge overlap with each other?
Rocking off each other.
Yeah, there's going to be a giant repulsive force at the very beginning of the simulation, okay? In fact, it's going to be so big, you're going to get particles traveling faster than the speed of light and everything's going to crash, okay? So, some people in the room have personal experience. So what we're going to do to avoid that is when we put particles in the box, we're going to put a particle, we put the second one, we're going to pick a right position, and then we're going to look at all the other particles to make sure they aren't too close to each other. And then if it's far enough from every other particle, we'll leave it. Cool. So this is just a little algorithm. This is not the only way of doing it, okay? But it's really the most obvious way of doing it. So what we're going to do is we have this placed flag in here, and while it's not placed, we keep selecting positions for the particle randomly in X and Y, and then we loop over. So here I have the outer sum is I, the outer loop is I, the inner loop is J, and I'm going to loop. The upper bound on J is just going to be I, which is the total number of particles I've already put into the system. Okay? And so just, I have a putative position for this particle here, and I'm going to look at every other particle and calculate the distance between where I want to put my new particle and the other particles, right? And that distance is just this square root of the sum of the squares. And if it's too close, then I have a too close flag, okay? And if I don't have a too close flag, then I can place the thing. Otherwise, I have to go back and do it again. So by the time I come out of this while loop, I will have a good X and Y position for my particle that does not overlap with any of the other particles. Cool? Yeah? Any questions on that? All right, so when I come out of that, I also have to give it a velocity, which again we're going to do from Maxwell-Boltzmann, which means I need a Gaussian random number, so I'm going to use the Fox-Muller transformation that we used before. And now my system is set up, okay? I have good initial position with no bad overlaps, and I have an appropriate distribution of initial velocities. Cool? So that's all just set up. I want to go through and do my integration, okay? And so what I can do is first I'm going to have a loop where I'm going to calculate all of the half-step velocities, okay, for all the particles. And then the next thing I need to do is figure out what my accelerations are equal to, okay? Well, here's the trick. Before, in the ideal gas, we just had all our accelerations equal to 0. But now our accelerations are not necessarily equal to 0, because if we have two particles that are within RC of each other, there's going to be a non-zero force pushing them apart, which means each of them is going to have an acceleration away from the other. Okay? But MD is so simple. All I need to do is go through, look at all the other particles. If I doesn't equal J, I can calculate the distance between them. If that distance is less than the cutoff distance, I calculate the force. This form here is obviously just the derivative of the potential. So the negative 12 comes down, and it becomes a 13, blah, blah, blah. Okay? And then once I have that force, I can take the x and the y component of that. And now I have my new acceleration in x and y. It's just that force over the mass. Cool? Is everybody cool with that? Because if you get that, you get molecular dynamics. That's all we ever do in molecular dynamics. Okay? Anything we want in the system, we implement it as a force. And then we just go through and calculate the force, include in the calculation of the acceleration, and go on numerically integrate. That's it. Cool? Yep.
You mentioned earlier bad overlapping.
Yeah.
Is that what R less than RC stands for?
No. So if R less than RC, so this is the cutoff. So if the distance between the particles is bigger than the cutoff, they have no interaction. Okay? So it's only when R is less than RC that I have to calculate this force.
So what do you mean by bad overlapping?
So what I mean by bad overlap is the potential increases as R to the 12, right? So this means that if you start your system, let's say you plop down a particle here, and you plop down a particle here, so that your separation between these particles is a small number. Well, you take 1 over a small number to the power of 12. Well, actually, to the 13th, because we're calculating the force. You're going to get a very, very, very big number. And a very big force is going to give you a very big acceleration. Okay? So if you start a system with two particles overlapping like that, they're going to have a massive acceleration. And so they're going to have a huge velocity out of your startup. So you start a system with an unbelievably high amount of energy in it. That is going to crash.
But aren't we assuming in the first place that they can't over each other?
So, but that's why when we start the system, we have to do those checks. So that if we plop down a particle here, it doesn't overlap.
Yeah.
Once the system is going, that takes care of itself.
Right. Because
particles, if they hit each other, okay, they kind of ride up that force curve and then ride back down. It's conservative force. Cool? As long as our time's up. Okay? Any questions on this? Because like I say, if you get this, that's MD. That's all it is. Yep.
Are we introducing a bias by the way we're initializing the position? Because there's no other random terms later, right? Like after the initialization, there's no random forces. So we're picking the position according to what we specified, but maybe that's not like a natural.
Right. So that's a very good question. Okay. So molecular dynamics, once you have your initial condition, in theory, it is deterministic algorithm because we do not include randomness anywhere else. We just do these calculations. In practice, things aren't so easy. Okay? In practice, you have a very complicated n-body interacting system. And so your trajectories are not stable. So if there's the smallest change arising from numerical error or slight differences in that setup, you get a completely different actual trajectory. Okay, that's why you can never use. Okay, and I'm going to say never here, looking into the next half a millennium. You can never use MD to say, I am going to make a picture of exactly what this system looks like in nature, and this is exactly the trajectory that it's going on. In our lifetimes, we'll not be able to say that, if ever. Okay? What you can say is, this is a good system setup representing this system. And if I let this run over time, or I do multiple instances of them, and I calculate some observable, that is a good measure of that observable. Okay? So even though it's deterministic in theory, in practice, you do not have predictive simulations. Cool?
If you use a small enough time step, could you just place them anywhere you want and over?
You don't, not if you have these giant force. You'd have to use incredibly small ones.
Yeah.
Okay? But even in pure MD, no, because you're starting with a massive amount of energy. Okay? So if you use a small enough time step and you have some way of draining that energy off, which we'll come to in a second, thermostats, then maybe. But it's still a bad idea. Okay? Instead, there's other ways of going about this. Let's say you start with a bad overlap. Just for a while, cap your maximum force. Just say the force can't be over this. Okay? And that way, even if it's a bad overlap, that they would fly apart at the speed of light, okay, they'll just move apart at some same velocity. Let that happen for a while. Everything is going to kind of come to a nice equilibrium. Then remove the cap and start your actual simulation. Okay? So that would be an equilibrium set. Equilibration set. Cool? Is this code okay with everybody? Okay? So that's really all there is to it. Then I just have to do the rest of the algorithm, right? I update the velocity, and yeah, so here I get the positions from the half velocity. I go through, calculate the acceleration with the new positions, and then I calculate, finally I calculate the velocity. Okay? This is just the velocity relay algorithm. Okay, in this simulation, I still have the old wall constraints that if a particle tries to go out of the wall, you just reverse the velocity. Can I do something else? Any ideas? With your newfound knowledge.
You could give the wall similar style
Potential. Yeah.
Just let them bounce off that.
Exactly. Okay. So let's just say that a particle comes to the wall here, and it's getting some distance of the wall. Let's just say, oh, there's a particle there, and you have the same WCA interaction, and you're going to bounce off. Okay? And we don't actually have to, you can actually, and a lot of the times you're required to do this for reasons, you can actually build this out of a bunch of particles and just fix them in place. And you can use the WCA potential to keep your free particles inside that volume. Okay? But you can also just define a mathematical boundary, and if you have a particle going like this, you can always just figure out the normal to the surface and how it's interacting with the center of the particle. So, okay? Yeah.
You make it out of particles, it's not really slow.
That is an optimization question. So yes, because you're adding particles to the system, but no, because what's nice about these particles is you always know exactly where they are. Right? So when you do a check, am I interacting with the walls, you don't have to look over all the wall particles, because you know where you are and you know where the wall particles are. So you do add a bunch more data requirements to your program, like where these particles are and stuff like that, but you don't add an expensive loop searching over space to find the distance. You always know where they are.
And since it's a continuous potential, it'll interact with more than one wall particle at once, right?
In this case,
So I guess
yes, it could. Yeah.
there's a weird geometry.
Yep. For sure. Yeah. But we'll see why it's sometimes useful to build things out of particles at the very end of the course. Okay? When we move away from the microscopic and come to the macroscopic, where we want to have something like friction. Okay? A smooth mathematical surface has no friction. We build out of particles because you have these dents like this, there's naturally a friction. Okay? Cool? Yeah, everybody okay with this? Any questions? So this is really MD. Cool, so now what I can do is I can do the exact same calculation for my pressure. Okay, that's the same at the bottom of the code here. Each collision contributes to this 2 times n times the velocity over the time step, and I can calculate the average force, and from that I can get the pressure. Okay, so let me see. Okay, so here is V and D of the thing. Let me clean it up. Okay, and now you can see so this is the XYZ file produced from the program we just looked at, okay? So now you can see when 2 particles come towards each other, they don't go through each other, they collide. Okay? And so now you can see all these more collisions, and so if you look at something near a wall here, look how often these particles are going to hit the wall here. Okay? They don't just bounce off once, go to the other side of the box, and not until then do they hit the wall again. No, they keep getting shoved back. Cool? So this is really all there is to MD, okay? The rest is all bells and whistles and tones. Okay? So, does it work? Does this whole excluded volume thing work and the van der Waals equation of state? Well, that program spits out an answer for the pressure of 0.221. Okay? That's a lot higher than we had previously, although I reduced my box size, so in an ideal gas, the pressure in that system would be 0.16, okay? Here, if you do the calculation with the van der Waals taking into account the excluded volume of the other particles, we get an answer of 0.24. Okay, so this is certainly higher than we had in the ideal case. And if you calculate out of the simulations, you get 0.22. Okay, which is close enough for our purposes. Okay, so yes, it does work out. Cool. Any questions on this? Okay, so this is a really powerful technique because what it means is you can take a bunch of particles that are under some kind of force, some kind of potential, and it's really easy to simulate what happens in time because you just calculate the net force on the object, you get the acceleration, you numerically integrate to get a new position. And you just do that over and over and over again. And you get a trajectory of all the particles in your system. Okay? This is why it's so widely used. Okay. So let's talk about a couple of the features of MD. We're going to brush up against a concept that it makes sense to just tackle right head on. And this is the idea of statistical ensembles of particles, okay? And I know there's a good reason for the word ensemble, but I'm not a huge fan of it in this context, okay? You really can think of these for our purposes as different system setups, okay? And so let's take the easiest setup, which is what we've been doing so far, which is the microcanonical ensemble. Okay, and those of you who have taken some statistical physics will recognize that term, I hope. Okay? You do not need stat phys to understand this simple concept. Basically, the question is, in our system, what parameters are being held fixed? Okay? So if we take a box alone, on its own, in the universe, somewhere out in space, okay? Like those poor guys from Superman 2 trapped in that weird mirror thing, okay? They're all alone out in space, and we have a bunch of balls bouncing around in there, okay? The balls can be interacting with themselves inside of the box in some manner or another, okay? But nothing is interacting with this box. Well, what's fixed in this system? Well, certainly the number of particles is fixed, right? The volume of this thing is fixed, okay? And because there's nothing interacting with it, the total energy in the system must be fixed as well, right? So this is the microcanonical ensemble. We have constant NV. Let's have a look at the canonical ensemble. So what we're going to do is we're still going to have our box here, particles bopping around doing stuff, okay? But now, one of the walls of the box, okay, can allow energy to pass back and forth, okay? So it could be a kind of rubbery membrane that you can hit from either side, and if you hit it from one side, you can give momentum to these particles, or particles hitting this side can give momentum to whatever's on this side. Okay. And what we make on this side, let's make it a giant bath. Okay, that is held at some fixed temperature. Okay, and this is massive compared to this. So any changes that happen over here have no impact on this. Okay. Now what is being held fixed? Pardon me? Mm-hmm. And it's still fixed because particles can't go through here, okay? Only energy. What else? V, okay? This thing can undulate maybe a little bit, but, you know, for all intents and purposes, it's the same volume. Anything else? Is energy still fixed? No. What's held fixed instead? Temperature. Right? Okay, so this is the canonical ensemble.
What's B fixed?
Well, because this wall, all these walls are solid. This one can move a little bit, but it's not like it's ballooning out like this and then shrinking back in. Okay? So in an ideal sense, this allows energy to go through it, but it still defines a fixed volume. Cool? So the dimensions of this box are not. Cool?
Well, I was just thinking, because in the previous example you did, your volume changes. These balls are getting
Here?
That one, that box right there.
Here?
Yeah, you said the volume is increasing, right?
No, I mean the total volume of this system.
Oh, right.
Yeah. Just the total volume of the system. That's all I mean by here. Okay? Not the available. Cool? So we're all in agreement here. So one point to note. What do I mean by fixed T here? Is this temperature actually fixed? Is it constant? What I mean is, if you measure the temperature in this small box at any point in time, do you expect that you'll get the exact same number?
The average.
Yeah. Okay. Really, when we say fixed T, we really mean that the average is. Okay. We still have fluctuation. you can get something coming in here that gives a kick to this, okay? And this is going to have a slightly higher temperature, but then it can have a big kick here, and that momentum leaves again, it can have a slightly lower temperature, okay? But because of this huge moderating influence, the temperature on average is going to be zero. Cool? So be careful when we talk about fixed. There are still fluctuations. Okay, we can also have the grand canonical ensemble. Anybody want to guess what happens here? Still have our box with particles bouncing back and forth.
Oh, that's like
Pardon me?
that's segregated.
That's a good idea. We'll come to that one in a minute. Okay? That's not what I want to do. So you're saying let's let E vary. Right? Okay, we'll come to that one in a minute. I don't want to let E vary. I want to let the other two vary. N, the number of particles. Okay? So let's say this has some connection to some other system out here. Okay, that particles can go through. And there can be an exchange of particles. Okay? So if the density of particles is too high in here compared to out here, there can be an exchange of particles through some path. This is the grand canonical ensemble. And in this, N is not fixed, but the chemical potential is. Okay? Which is the energy per particle. You can still have a fixed volume. Okay, this can still be a fixed volume. And I mean, this can act as a heat bath, okay, through this exchange. So we can still have a fixed. Cool. Okay. This one, that's mu for chemical potential. You remember that from biophys, right, Matt? Okay, now let's take Alberto's suggestion, okay, which is to let the volume vary, okay? So I'm still going to have this membrane here that can exchange energy, okay, but it's not allowed to exchange particles. And now what I'm going to do is I'm going to have a system where the dimensions of the box can change, okay? And so here, what's being held fixed? This isothermal, isobaric. And so what we'd be holding fixed is N, P. Okay? So if this was equilibrated with some pressure outside, okay, then whatever's going on inside of here, the volume can adjust so that the pressure is constant. Cool? So ensembles is just really fancy way of saying these different system setups, okay? Now in statistical physics, they're unbelievably important because you can develop the forms for the free energy according to all of these, like the Helmholtz free energy, okay? And from that Helmholtz free energy, then you can determine a lot of the properties of your system, okay? For our purposes, we're just more interested in knowing what do we do, how do we do a simulation that corresponds to these different scenarios? Cool? So that's why I'm introducing. Well, we've already done this simulation, haven't we? Because we had a bunch of particles isolated in the system, fixed N, fixed V, and fixed energy, right? Because by conservation of energy, whatever kinetic energy we put into the system, the velocities we give to the particles, and whatever potential energy is in there, and this is where the idea of the bad overlaps comes into play. Because if we have bad overlaps, we start with a lot of potential energy that would go into kinetic energy. That's why they travel so fast, okay? So that energy is constant. What if I want to do this one? And obviously, this is super important. Why would it be so desirable to have a fixed T instead of a fixed E? Can anyone think of examples?
Much easier to hold T fixed in the lab than T.
Yep. So it's more realistic because most systems interact with another system. It's not often you get to experiment on the Superman guys in space. Okay? Anything else?
Well,
So that's a huge reason, right? We're often connected to some kind of heat bath, right?
doesn't the amount of energy that we have in your system usually reflect the temperature we're at?
Yes, okay? But here's the question. Let me rephrase the question to address that point, okay? Can you think of a scenario where having some kind of control over the temperature would be important to have a realistic simulation? Where if you just had an isolated system, microcanonical ensemble, okay, or you had the energy in the system, things might go a little crazy. Yep.
Any exothermic system, if you're releasing energy in the system, you want to release that energy to the
Exactly. Excellent answer. Okay. So if we start with the system that has a fair amount of potential energy in it, that potential energy is going to go into kinetic, right? Because equipartition, which we'll talk about next, we have an equal sharing between potential and kinetic energy. And so if that goes into kinetic energy, all of a sudden everything in your system is moving really fast. But this doesn't happen, let's say, in your body, okay? Because you're connected to heat baths. Things stay at the same temperature. Okay, so we need a way to dissipate that extra energy coming from potential. Okay, cool. Along those lines, any other pictures that might also be the case?
Well, if you had endothermic processes, maybe self-assembly or something, you're forming structures, you're forming molecules, you know what I think breathes.
Right, so same idea. Yeah. Anything else?
If you want to look at a specific phase of the material, you want to keep it
Temperature
constant.
Yep, great. Anything else? What if you have like a non-equilibrium system? Let's say you have an external field on your system that's driving some charged particles through the system, right? You're inputting energy into your system, right? Driving them through, hitting those water molecules, giving them extra momentum. Everything's heating up in time, okay? If you don't have some kind of temperature control in there, your system's getting stronger, okay? So it's often desirable to have a fixed temperature because we need a way to drain off all of this energy we're talking about. Cool? Okay. So that, by the way, is Joule heating, where you add heat to your system by applying an external field that makes stuff move, basically. Cool? Yep.
The last system we looked at, the isothermal isobaric, is that an isothermal isobaric ensemble?
Yeah. Yeah. Okay, so the question we have to answer here is, can we control the temperature in our simulations? Okay? And this is the idea of thermostating our system. All right? Yeah? Okay. Any ideas of how we can, what's an idea to thermostat our system, control the temperature? Any ideas? If this was on an assignment, and I told you write a simulation where you control the temperature in your system, what would you do?
But every time a particle hits the wall, if it hit it really hard, it just just reduce its speed or increase its speed closer to the average temperature of the wall.
Right. Temperature is essentially the kinetic velocity or the kinetic energy of your particles, right? kinetic energy of particles is the velocity. So if you have too high a temperature, why don't we just scale down the velocity? Okay, so this is thermostating by velocity rescaling. Okay, and the idea is that we will talk about this next class, equipartition. The average v squared you can derive to be d, where d is your dimensionality, i.e. 1d, 2d, 3d, that's kt over m. Okay? And so if you want to keep this at a fixed velocity, what can you do? Well, you can say your input velocity, okay, you want to modify the velocity of any particle vi, so let's call that v tilde, and the ratio of that to the original velocity is going to be the square root of t naught over t. Okay, and so we can call this that vi tilde equals some scaling factor, lambda, times vi. Okay, should really be the magnitude of this.
What's the tilde?
That's the rescaled velocity. Okay, so we look at our system, we have a bunch of VIs. We want to change all those VIs to be this new, to give us the proper temperature. Cool?
What's D?
D is the dimensionality of our system. 1D, 2D, 3D. Okay, so we can do this at every time step, and we'll get exactly the same temperature at every time step. Is there a problem with this?
It suppresses fluctuation.
Yeah, it suppresses fluctuation. Okay, we always have exactly the same times, the same temperature. Okay, this is not, as we talked about before, when we talk about a constant temperature, it's not that it's always the same number, but that the average is that number. Okay, there can be fluctuations in that temperature. Those fluctuations are important. Okay, so to get around that, let's have it not quite so tightly coupled. And this is the Berenson thermostat. And so instead of having that tight coupling, let's instead change the temperature of the system at some rate which is proportional to the temperature difference, okay? Between your target temperature, T naught, what you're currently at, and we can include a time constant. Okay, so the Berenson thermostat is very common in ND simulations. And so what you would see then, if you were to solve this differential equation, what would you expect your temperature as a function of time to look like? An exponential, okay? So you're at some temperature, and here's your target temperature. You decay towards that target temperature with a characteristic time tau. Okay, so changing tau allows you to change how fast you approach your target temperature. Cool? So this means that you instantly don't go to your target temperature. Okay? So you can still have some variation in T while maintaining the correct average temperature.
Oh, we're not looking for constant temperature, we're looking for constant average.
Yeah.
Right.
Cool?
How do we choose how?
You look in the literature. You don't want it too tightly coupled because you don't get fluctuations. But if it's very loosely coupled, then you're never going to be at the right. Right?
There's no natural way. It just seems like we're kind of
Sure, you can do some dimensional analysis. Right? This is a characteristic time. So
Oh, I see.
what's the characteristic time for energy dissipation? Yeah.
Okay.
I was just wondering, why do we need to rescale the velocity?
Well, because we want to control the temperature, remember? So let's say we're trying to simulate something at, room temperature, and we calculate the temperature in our system, because remember, you get the temperature in your system by looking at the average velocity of particles in your system, right? Temperature comes from kinetic energy. Cool? Yeah? Okay. There is a very interesting problem with this. Okay? When you use the Berenson thermostat, you must be very careful. What you must be careful about is that you apply it to the internal coordinates of your system and not the global coordinates. What do I mean by that? If you have a bunch of particles, let's say some of them are joined by springs, some of them are not, they're all moving around, okay, some of them are rotating, things like that, okay? You can have a global center of mass translation and rotation in your system, okay? If you do not periodically remove that, what happens is that the energy from, let's say, the fast fluctuations in this vibration get funneled into the lower frequency modes of just the translational or rotational motion. Okay? And what happens over time, if you start with a chunk of water in a vacuum, and you let it go with velocity scaling just on the global velocities of those water molecules, over time, you end up with what's called the flying ice cube. Because all the internal energies of those things vibrating and stuff like that gets pushed into the mode of just moving along. So all the water molecules stop in space, and they just move as a collective in one direction. Hence the flying ice cube. Okay? Very famous paper written on this. Okay? On the flying ice cube. All right? The way to correct that is to apply it to the internal coordinates. So what you can do is, for any velocity, you can calculate the center of mass velocity, remove that, and apply the scaling to that velocity. Okay? There's an even simpler way: just remove the center of mass motion from your system. Okay? So this is a feature in empty packages: remove center of mass. And if you're using this type of thermostating, you want to periodically remove the center of mass. Otherwise, you'll get these crazy things. Cool? Okay.
And that problem is coming from
I don't want to get into the technical details, okay? Because it's beyond, right? It more comes out of this one the way it's in. Yeah, not this one. The problem with this one is no fluctuations. Okay? Look up the flying ice cube. In fact, you can even look it on Wikipedia. Okay? Okay, any questions on this? Okay, so we're getting somewhere. We have some thermostating algorithms. We have to be careful. There's another problem with the Berenson thermostat. It gives us fluctuations, but we kind of just threw those in there. And we even have flexibility in this tau parameter. So we're not guaranteed that these are the correct fluctuations for our ensemble. Right? There's no guarantee of that. Well, in fact, the Berenson thermostat gives us fluctuations, but is not a proper canonical ensemble. All right? In many cases, it does the job. But if you're really trying for a detailed statistical calculation, this is not fully proper canonical ensemble. Cool? So, this is one way of controlling the temperature in the system, scaling the velocities. Can anyone think of another way you can control the temperature of the system? And you can try and take motivation from pictures we drew up there before when we were talking about the ensemble. So in an actual physical system, how is the temperature controlled?
Since all of the processing thing is increasing, right?
Well, the pressure is not so easy. That's more of an observable than an input parameter.
What about the forces experienced by the particles that are being kicked by, say, the water molecules in there?
Right. So another way of saying what you're saying is the temperature is moderated by these interactions with the heat bath. Right? So why don't we just routinely pick some particles and say, you interacted with the heat bath, and change something about it. We can change their velocity because they had some kind of collision. Okay? We can change, pardon me? Yeah, but if we're in contact with a heat bath, these things are changing that way. Okay? So this is called a stochastic thermostat. Yep.
So like randomly choosing which ones to rescale.
Not even rescaling.
Just setting.
Yeah, what we can do is we can say, okay, we have a heat bath over here that has a certain distribution of Maxwellian Boltzmann distribution velocities. Let's take a particle from our system and let's just make its velocity to be one of these. Cool? So that it's undergone a collision. Okay, this is a stochastic thermostat, and we'll begin tomorrow talking about those. All right. A lot of things are weird, doesn't mean they aren't useful.